included in your syllabus as a separate module, and that is what we are going to start today. Again, I'm going to go a little slow in the beginning today, but in next week's class this will be over. Like I need only, after today's class I need only one more class to finish the syllabus. But please follow this very closely, because some very new concepts are going to be introduced which are extremely important. Okay, understanding them are extremely important. So the contents of this module are going to be like this. This is basically the formalism of quantum mechanics. We are not going to solve problems, but we are going to understand how quantum mechanics is has been built, what mathematics is required to understand quantum mechanics. So these are the things that we will discuss: operator formalism, idea of Hilbert space, observables, determinate states, eigenfunctions of Hermitian operators, simultaneous measurements, uncertainty principle, and two more things which I have not been able to include in the slides. In fact, in today's class, we will study only till Hilbert space, and your syllabus starts with the mention of this only, simultaneous measurements. But you cannot go to simultaneous measurements unless you have a concept of these things over here. So we will go through these things, discuss these, and then go to the actual discussion of simultaneous measurements. This is extremely important, as I told you earlier also. Okay. All right. So first of all, let us see what is operator formalism in quantum mechanics. We dealt with this very briskly in one of our earlier classes. So what is an operator? All right. It's just a mathematical rule to transform a given function. If you are talking about it mathematically, an operator is simply a mathematical rule to transform a given function. All right. So this is a typical operator equation. O is an operator. It acts on a function psi x and it gives a transformed function phi x. So depending on what psi x is and depending on what kind of operator O is, we will get a transformed function phi x. All right. So suppose we take an example where psi x is equal to x to the power n. Okay. So this is all very trivial algebra that we are doing, but knowing it in terms of operator is important. So I have just made a table of what different operations will result in when they act on this function psi x equal to x to the power n. All right. So for example, square root will give us x to the power m by 2. Multiplication by a constant ax to the power m. Differentiation, this. Integration. So all this you know. All right. I'm just trying to uh, instigate the concept that all this we have been doing since probably class 7 or 8, at least taking square root and multiplication in algebra, and then in our high school we have done differentiation and integration. But these are simply different forms of this operator equation. An operator acting on a particular function, transforming it to a different function. All right. Now, why do we want to discuss about operators so much? Because we have earlier seen that each dynamical variable in quantum mechanics is represented by a particular operator. All right. Okay. Now, let us see what operator algebra is like. All right. First of all, how do we perform addition and subtraction with operators? Very simple and totally understandable. Suppose you have two operators A and B. If the sum of them is operating on a function psi, then it is a simple distributive law, A psi x plus B psi x. Subtraction also similarly, A psi x minus B psi x. Alright, simple, understandable and known. Next, multiplication. So here is where the new concept comes in. Multiplication of operators is not the same as multiplication of algebraic expressions. Alright. So suppose we have two operator equations. A psi x gives us phi x, and then if we operate another operator b on phi x, it gives us a new function fx. Alright. Please, at any point of time, if you do not understand anything, unmute yourself and ask me, because these are very, very important concepts that are being discussed right now. Alright. So now, if we consider B and A together, so sort of a product of B and A operating on the function psi x. But we know A psi x is phi x, so this is nothing but B operating on phi x, so that the result is fx. Simple. However, A operating on B psi x is not fx, because B fx is fx, B phi x is fx, B psi x we don't know what that is, and A operating on B psi x we don't know what that is. So although B product with A operating on a function we know the result, but A operating on B then on A product with B operating on the same function does not give me the same result. So this is very, very important, because this is where operators become different from algebraic expressions. Addition and subtraction, it seems that operators and algebraic expressions are same. But the moment when you go to multiplication, you see that operators differ from algebraic expression. In general, the product AB is not equal to the product BA. Okay, and this is where we get a very, very new but an extremely important concept of commutators. The fact that AB not equal to BA when you are dealing with operators gives us a new mathematical concept which are known as commutators. Okay. So suppose in a special case, in general AB not equal to BA. Suppose in a special case AB is equal to BA. We say that the operators A and B commute. Okay. If AB is equal to BA, we say A and B commute. And by definition, a commutator is represented like this. Okay. Third bracket A comma B, and the expression is AB minus BA. Alright. As you can see that when operators commute, AB is equal to BA and the commutator is equal to 0. So when you see the commutator of two operators is 0, you can say that they are commuting operators. They commute. And when the operators don't commute, AB not equal. Yes. Hello. Hello. Is everybody online?
ম্যাম কারো মাইক অন আছে?
Yes, ma'am.
অফ করে দিয়েছি।
আচ্ছা, আমি যেগুলো বলছি তোমরা বুঝতে পারছো তো?
হ্যাঁ।
Okay.
है मैम.
So if A, okay, so if AB not equal to BA, we say that the operators do not commute. Okay. Okay. So we get the new concept of commutators, and we will do two examples just to show the uh, the circumstances or the instances, the examples where operators may or may not commute. Okay, I'm taking some time in introducing this because commutators will ultimately form the basis of our concept of simultaneous measurements. Okay, so suppose in our first example we have an operator A ddx and another operator B d2 dx2. All right. So AB acting on psi x, first d dx, then d2 dx2 acting on psi x. So it is d dx acting on d2 psi dx2, and the result is d3 psi dx3. Clear? Next we have to see what BA psi x is. Again, now we first have d2 dx2, then we have d dx, and this gives d2 dx2 acting on d psi dx, which again gives us d3 psi dx3. So AB acting on psi x gives us d3 psi dx3, as well as BA acting on psi x gives us d3 psi dx3. So according to the definition of the commutator, AB acting on psi x, which is AB minus BA psi x, we get AB psi x is d3 psi dx3 and BA psi x is d3 psi dx3, which of course is equal to 0. Now, since psi x is not equal to 0, because otherwise, I mean, that would lead to a trivial case, the only possibility is that the commutator AB is equal to 0. Therefore, the operators ddx and d3dx3 commute. So this is an example where two operators ddx and d2dx2 commute. Okay. Now we take another example where we take one operator as x and the other operator as ddx. Okay, so operators are similar, but we'll see what happens in this case. So now AB psi x is simply first x, then d dx acting on psi x. So it's simply x d psi dx. But when you take BA psi x, you have first d dx and then x and then psi x. So it becomes d dx of x psi x, which is equal to, if you differentiate by parts, it becomes psi x plus x d psi dx. All right. So AB psi x is x d psi dx, but BA psi x is psi x plus x d psi dx. So according to the definition of the commutator, now this, if you put the two values of AB psi x is x d psi dx and BA psi x is this psi x plus x d psi dx. So these two cancel out and the result is not 0 but minus psi x. Okay. So now we have equating AB commutator psi x and minus 1 psi x. The commutator of A and B is equal to minus 1. So in this case, A and B are operators which do not commute. Okay. So I've given you the definition of commutators, and I've also shown you using commutator algebra how we can show when two operators commute and when two operators do not commute. All right. So we will have much more on commutators later on. For the time being, I just introduced the mathematical concept, and later on we will see what the physical interpretation of commutators are in our next class. All right. Now we will quickly go through the types of operators. What are the different types of operators that we are going to encounter in quantum mechanics now and later on? Okay. Or in general, what are the kind of operators that exist? First of all, a linear operator, the simplest kind of operator. This is what a linear operator is like. A operating on C psi x gives C A psi x, that is AC equal to CA, where C is a constant. So only when this relation is followed by a linear operator, we say we say it is a linear operator. Okay. And you can see that any linear operator commutes with an arbitrary constant. If C is a constant, then AC equal to CA always, any arbitrary constant. In general, for linear operators, these rules are followed. A plus minus B into C is AC plus BC, that is the distributive law, and AB into C is equal to A into BC, that is the associative law. All right. Okay. Next, we may encounter the null operator. Simple, A psi x equal to 0. That is, an operator when operating on a function results in 0, reduces it to 0, we say the operator is a null operator. Inverse operator, very important concept. Okay. Suppose we have the linear operation, an operator t acting on a function psi gives phi. So we can write in this case psi equal to t inverse phi if t inverse exists. Then this t inverse is called the inverse operator. Of course, 1 by t or t inverse must exist in order to be called an inverse operator. Identity operator, again very important. We represent it by I. So an operator acting on a function, if it gives the function back, we call it the identity operator, much like the number 1 in linear algebra. Okay. Singular and non-singular operator, again very important concepts that you should have. Now suppose we have two operators such that AB equal to BA, that is they commute, and the product is equal to the identity operator. Okay. So we can write in this case that A inverse equal to B and B inverse equal to A. Alright. So if such reciprocals exist, then we say the operators are non-singular operators. If the reciprocal of an operator exists, we say the operator is a non-singular operator. On the other hand, if suppose A psi x equal to 0, that is a null operator, and psi x is not equal to 0, then of course you cannot have A inverse at all. Okay, A inverse cannot exist, and then we call it a singular operator. Okay, so when you are dealing with operator algebra, you must first know whether an operator is singular or non-singular before you take its inverse. All right. Next is Hermitian operator. I am sure all of you are finding some familiarity with matrices that you had done in your first semester. You had done matrix in your first semester, right? So I suppose you can find some familiarity with the concepts of matrices that you have already done in an earlier semester. Hermitian operator, once again very important. It simply has to satisfy a rule. If an operator A satisfies this relation, what? That psi n star, product of psi n star with A operating on psi m and integrated over all space is equal to product of A operating on psi n whole star into psi m integrated over all space. If an operator satisfies this relation, then we call it a Hermitian operator. Of course, psi n and psi m are both eigenfunctions of the operator A. Sorry, because there is some typing deformity over here. Psi n and psi m are both eigenfunctions of the operator A. Alright, then it is called a Hermitian operator. We have to remember, very important, and that is why I put it in caps, Hermitian operators are linear operators, the first kind of operator that we discussed, and Hermitian operators always have real eigenvalues. Eigenvalues of Hermitian operators are always real. Okay, I'm sure you've done this in matrix operations, that Hermitian matrices have real eigenvalues, and same applies here. Next is the concept of an adjoint or Hermitian conjugate of an operator. Okay, two operators A and A dagger, if they satisfy this relation psi n star A dagger psi m equal to A psi n star psi m, then we say A dagger is the adjoint or the Hermitian conjugate of the operator A. Okay. Then we have the parity operator. A parity operator reflects the function in its coordinate. That is, pi here is the representation of the parity operator. When it operates on psi x, it gives us psi of minus x. Okay. Again, an important physical concept which we will require later on. And finally, we have the unitary operator. Okay. Inverse and adjoint are same. If an operator is such that its inverse and adjoint are one and the same, we call it an unitary operator. Of course, u dagger u is equal to u dagger equal to the identity operator. Okay. We have to remember that the product of two unitary operator is also a unitary operator, and I have done this proof in the notes that I have sent you. Okay. Now, we will not require these operators directly in what we are going to do next, but we are going to use these terms, Hermitian and linear and Hermitian conjugate. These terms are going to be used several times, which is why you should have a sound concept of what these terms relate to. And that is why I have gone through this list of different kinds of operations that are there. Okay. The final concept that I'll do today, and this is where I'm going to end because I want to go a little slow. I don't want to, I want you to understand bit by bit of what the new ideas are being put forward. So this is the idea of Hilbert space. I'm sure many of you, those who browse a little bit of scientific literature on the internet or have read through a few reference books, have come across this term Hilbert space. Okay. If you know what a vector space is, then you must know that Hilbert space is a subset of the linear vector space. All right. And why are we discussing this at all? Because in quantum mechanics, we deal with wave functions, and we will see that there is a very close relation of the Hilbert space with the wave function. All right. Now, the subject we are discussing is quantum mechanics. All right. And in quantum mechanics, you have been observing till now that we deal with two things. One is the state of the system, and the other is the observable or the dynamical variables. All right. Now, the state of the system is represented by a wave function, and the observables or the dynamical variables are represented by operators. Now these wave functions are basically abstract vectors, okay, and the operators are basically linear transformations. So quantum mechanics speaks the language of linear algebra. The language of quantum mechanics is simply the language of linear algebra. Okay, the little bit of vector space and sets that you have done is the language of quantum mechanics, because here we discuss the state of a system represented by a wave function, which in turn is basically an abstract vector, and we talk about the changes brought in the wave function by an observable or a dynamical variable, which is represented by operator, and operators, as we have seen, are nothing but linear transformations. So basically we are talking about linear transformation of abstract vectors. So quantum mechanics speaks the language of linear algebra, and the only difference is that till now you have worked with algebra in three-dimensional space, three variables x, y and z. But now we have to think about working in the n-dimensional space. We have to cover all of vector space in doing the linear algebra when we are talking about quantum mechanics, and that would be the n-dimensional vector space. But there is no need to be alert or afraid when you hear about the n-dimensional vector space, because here Hilbert space will come to our rescue. Why? We'll see in a moment. Okay. Now in the n-dimensional space, we will switch our representations. Okay. From now on, the mathematics that we are going to do will be in the n-dimensional space, and therefore we are going to replace our earlier representations by some new notations. Okay. Please get this very clear. Now a vector will be represented like this. Okay. This is known as the bracket notation. Bra and ket, the bracket notation. Okay. So this is the new representation of a vector, and we know that in the n-dimensional space this is a column vector. Okay. So A1, A2, etc. up to AN are the components of the column vector in the n-dimensional space. If you want to take the complex conjugate of the vector, you simply reverse the direction of the bracket. Okay. And this actually represents a row vector. So a vector is represented by an n-dimensional column with n components. Its complex conjugate is represented by a n-dimensional row, where each component is represented as a element of this row. Okay. Only now the elements will be complex conjugates of the elements of the column vector. All right. And we know the three-dimensional dot product, ax, ay, ax, bx, ay, by, az, bz. In the n-dimensional case, this will be known as the inner product. Okay. And the inner product is represented like this. A, B equal to A1 star B1, A2 star B2 plus etc. up to AN star BN. Alright. So this is the inner product. We will require this several times in our further discussions. So please have this concept very clear. Vector represented like this. Whenever you see this notation, it means a vector, the column form. Its complex conjugate. So whenever you see this notation, the reverse bracket, it's a row vector. And this AB in this notation means simply the dot product or the inner product. All right. And all linear transformations, that is the operators, are now matrices, and a transformation equation will read like this. So an operator T acting on a vector A gives a vector B, right? So it will be like this. An operator T is an n cross n matrix acting on a n cross 1 column vector, giving us another n cross 1 column vector B. Okay. But again, please don't be, afraid, or don't think about skipping this, because we are not going to deal with n cross n matrices. We are simply going to deal with these notations, and dealing with these notations, I assure you, is much simpler than dealing with integrations. The bracket notation of quantum mechanics is the simplest form, and it makes life much easier. I am assuring you of that. You just need to do it a few times in order to get, a feel of it. And then it becomes pretty easy. Once again, just vector. Whenever you see this, it means a vector. Whenever you see this, the reverse of this, it means the complex conjugate of a vector. And whenever you see this, it means an inner product. Okay. And operator acting on a vector gives another vector. Okay. All right. Remember, however, that in quantum mechanics, these vectors are actually functions. We deal with wave functions, right? So it is the wave functions that we are going to represent by the vectors. So instead of n dimension, we have to conceptualize the infinite dimensional space. Remember, whenever we perform the integrations, we integrate from minus infinity to plus infinity. So when you were integrating in the different problems from minus infinity to plus infinity, you were actually spanning infinite dimensional space. So you have already worked in the infinite dimensional space without specifically mentioning so. Okay. You just have to remember that functions, continuous functions, they exist in infinite dimensional space. So a wave function that we have so far dealt with, we know that if it is to represent a possible physical state, it has to be normalized, because only a normalized wave function means that there is a certain probability of finding it at a particular point of time. And normalized wave function means its probability density should be equal to 1. So this is what we have already seen, and we know that such functions are square integrable. All right. Now, when a function is square integrable, then the set of all such square integrable functions such that they follow this rule, that is minus infinity to plus infinity mod fx squared dx is less than infinity. So this falls in this category. This square integrable function equal to 1 is of course less than infinity. So it is a subset of all this, the set of all these functions. So the set of all such square integrable function, they constitute a vector space called the Hilbert space. Okay. So you've heard about Hilbert space so much. This is what Hilbert space is. It is a subset of the entire vector space, and it consists of square integrable functions. So basically, in quantum mechanics, the wave functions which have to be square integrable if we want to make them represent physical states of certain particles, they basically exist in the Hilbert space. So when you are dealing with functions, wave functions in quantum mechanics, you are already working in Hilbert space. So all the problems that you have so far done, you have already worked in the Hilbert space, although unknowingly so. Okay, and in the Hilbert space, the inner product is nothing but this. This is the inner product. It is nothing but this integration, and you have done this integration so many times. All right. And so in the Hilbert space, since we have already seen that this is what the Hilbert space is formed of, their inner product is bound to exist here. So we have been dealing with this, but we had not earlier mentioned the name Hilbert space. Okay, so we just have to remember that from now on, whenever we are speaking of Hilbert space, we are basically speaking of the region in which the wave functions representing a quantum mechanical particle exist, and therefore their inner product always exists in this region. All right, we will talk about more on this, and as we explain the different physical conditions, the things will become clear why we have been discussing these abstract concepts now when we are at the end of our syllabus, when we finally move over to the discussion of simultaneous measurements. All right. Okay, now I have taken most of, if not all, I have taken most of these concepts from Griffith's book. So like the earlier time when I discussed the concept of probability with you, once again I'll scan the pages of Griffith that are relevant and send it to you via mail. Okay, because that will help you if you even go through, even if you read Griffith's book like a storybook, it gives some it improves your concepts very much. Okay, so it will heavy